Hello and welcome to the Moxy tutorial series. This lesson covers oxygen delivery response time. This presentation is going to cover how the oxygen delivery systems in the body respond to changes in load. Understanding of these principles will help discern when changes in SMO2 or THB are caused by oxygen delivery systems or oxygen utilization systems. Let's first review some concepts from earlier lessons. In the Introduction to SMO2 lesson, we looked at how SMO2 is a measure of the balance of supply and demand for oxygen in the muscle. In the bioenergetics section, we looked at how oxygen utilization starts and stops almost immediately with the start and stop of loads. Now we're going to look at how the oxygen systems respond to changes in load, and we're going to see that it responds more slowly than utilization. The flow of blood is how oxygen is delivered to the muscle. The total blood flow available for the entire body is called cardiac output. The fraction of the cardiac output that gets delivered to the muscle is dependent on the vascular tone of the muscle and the vascular tone in the rest of the body. The cardiac output takes about 1 minute or so to respond to a change in load. The vascular tone in the muscle and the rest of the body can change over time lengths ranging from seconds to several minutes. Cardiac output is the product of heart rate and stroke volume. Heart rate typically increases linearly with load. Stroke volume, however, can have a more complex relationship with load. This means that the heart rate is not a direct indicator of cardiac output. Of course, heart rate is much easier to measure than cardiac output or stroke volume, which is why it's used more often. In cases where the body is reacting to a change in load, the response time of heart rate can be a good indicator of the response time of the cardiac output. There are several heart rate response times that should be considered. First, the heart rate may start to increase even before the start of the load, just in anticipation of that load. This can drive a small increase in SMO2. At the onset of load, it takes the heart rate about 1 to 2 minutes to reach a steady state in response to the load. This portion of the response time is representative of how long it takes the oxygen delivery system to respond to the increase in load. In some cases, the heart rate may change over a period of minutes. In these cases, we cannot infer that the blood flow in the muscle is actually increasing. A long, slow heart rate increase like this can be concurrent with the reduction in stroke volume or even a change in vascular tone in other parts of the body. Finally, when load is stopped, the heart rate takes 1 to several minutes to return back to a baseline value. When we understand the difference in response times between oxygen utilization and oxygen delivery, we can use this to help view utilization and delivery separately by introducing a sudden change in load in our assessment. At the sudden onset of load, we can see oxygen utilization by itself by looking at how quickly the SMO2 drops. At the sudden stop of load, we can see oxygen supply by itself by looking at how quickly the SMO2 increases. This concept is one of the drivers for introducing the 1-minute rests in that 5-1-5 test, which will be discussed further in more advanced lessons. This graph shows an example from a 5-1-5 assessment. The 5-minute durations of the low SMO2 are the loads, and the 1-minute peaks of the SMO2 are the rest periods. The increasing height of the peaks as the load increases is indicative of a strong oxygen supply system. When the load is removed, the cardiac system is able to completely restore the oxygen levels in the muscle during those 1-minute rests. This graph shows another example of a 5-1-5 assessment with the same pattern of 5 minutes of work and 5 minutes of rest. This time, however, the height of the SMO2 peaks during the rest periods starts to decline at the higher loads. This indicates that the cardiac system is not able to completely recover the muscles during that 1-minute rest. This graph shows a close-up of one load from a 4-1 intermittent load assessment for a cyclist. This assessment is a series of 4-minute loads with 1 minute of rest in between. SMO2 is on the left vertical axis with heart rate on the right. A new load or set is started at the 25-minute point on the left side of the graph. Note that it takes about 90 seconds or so for the heart rate to reach a stable value after starting the load. The vastus lateralis, or VL, is one of the largest working muscle groups for cyclists. Note how the SMO2 rapidly declines immediately when the load is started. This is indicating a very strong utilization of oxygen. Note as well how the SMO2 in the VL increases slightly as the heart rate continues to increase towards a stable value. The response in the biceps is also very different. The SMO2 in the biceps declines much more slowly for a longer period of time than the VL. The biceps have some involvement in stabilizing the cyclist, but it works much less than the VL, so its oxygen utilization is also much less. By introducing a rest period into the assessment, we were able to see differences like this that disappear once the athlete reaches a steady state. In this lesson, we looked at how the oxygen supply system has a delayed response to changes in the loading on an athlete. This effect can be used to help differentiate effects from oxygen delivery and oxygen utilization. Thank you for taking time to view this tutorial.